Welcome to the presentation of an empirical study of the NTFS cluster allocation behavior over time. It's written by me, Martin Karresand, and Professor Geir, Olav, Dyrkolbotn and Professor Stefan Axelsson, all of us from the Norwegian University of Science and Technology. The work is really a continuation of previous work. I presented part of it on the last year's DFRWS USA, and this is a further use of the data from experiments done then. The main reason for doing this job is that the digital forensics community is flooded with data, especially within the file carving community. Although there are different projects, many of them going on, trying to improve the algorithms used and in that way make the process of file carving more efficient. Our approach is, and is as far as we know, we're the only ones, is focused on trying to utilize the data more efficiently. We're not saying that we want to skip any data, but if we try to find the most probable position of user data, for example, in a hard drive, we should start in that area. And if we don't find what we're looking for there, we can go on and look in other areas instead. Currently, as you know, we start from the beginning of a disk and linearly progress towards the end, trying to find what we're looking for. And we mean that in that way we miss out on certain things because we're looking at, for example, the operating system, which is at the beginning of a hard disk. So, as we suggest, look at the position where it's most probable to find what you're looking for. Another reason for this work is that Brian Carrier, who wrote File System Forensics in 2005, which has been the Bible of file carving. It's being a bit outdated now. His findings or his writings on Windows NTFS is based on Windows XP. And as you all know, Windows 7 is now outdated. So there's been a lot of things happening since then, and therefore we want to update the knowledge on NTFS in this way. Of course, we have also looked at, or at least tried to look at, the possibility to use the pattern of allocation to help or improve the timestamps of the file system. Timestamps can be forged, manipulated, and therefore if we can combine the knowledge of the timestamp with knowledge on the behavior of the allocation algorithm, we can see from the pattern that one file is probably written before another one, although the timestamp says something else. Some work has been done by Sven Villasen, who wrote a PhD dissertation or a thesis on timestamps, but he only looked at it in the theoretical way and said that there are certain circumstances that has to be fulfilled before you can do this. We have, as I said, looked slightly at this, and once again the main reason being that we want to improve file carving and other digital forensic processes by utilizing the data in a better way. To do this, we have done an experiment. I described it slightly last year and I will repeat it this year. We used 32 virtual machines, VirtualBox machines, running 4 different versions of Windows 7, 8, 8.1 and 10. We also use 2 different sizes of hard drives, 64 gigabytes and 256 gigabytes, just to see if there are any differences between the allocation behaviors depending on the size of the disk. We intend to run 10,000 operations. Many of the machines reached that goal, but unfortunately some of them were slower than others, and we had to stop the experiment after 16 days because we were running on a cluster that we had borrowed from the Swedish Defense Research Agency, and we ran out of time. Each iteration of these 8,300 iterations consisted of a full power cycle. So we first powered on the virtual machine. We then did a file operation, switched off the machine, and extracted the bitmap from the hard drive. The hard drives were virtual static hard drives, and they emulated mechanical hard drives, all of them. The bitmap copies were then used to calculate deltas between each file operation. The file operations could be one of the four of writing, deleting, increasing or decreasing the size of a file. All of the writings were also stream writings. There are two ways of writing a file. Either you write it as a stream where the operating system doesn't know the size of the file, so it behaves in a certain way, or you can write it as a block, and then the operating system knows beforehand the size of the file and therefore can allocate in a way a certain area to the file, or at least it knows when it ends and how much data it is and can allocate in another way. But as I said, we used stream writing for all of the writing operations. So we have some results from the experiments. And first of all, we have lumped together, grouped together Windows 7, 8 and 8.1 and separated Windows 10 because we found there were differences between those two groups of operating systems. Also, what I'm going to present is the results for the 64 gigabyte disks, since the 256 gigabyte disk didn't have any differences towards the 64. We scaled each file operation with a factor of 4.6. And they were equal, or I should say similar, not equal. They were similar in appearance, so there are no differences in allocation behavior between different sizes of disks. Well, to the graphs then. We start with the median position of the allocations. We have also, of course, calculated the mean, but since that's a calculated value, we didn't see what we see in the median position, which is an actual value. There has been allocations at that specific position that the median gives. And as you yourself can see, to the left, all of the graphs to the left will be for the group Windows 7, 8 and 8.1, and to the right we always will have Windows 10. The Windows 7 group, as you can see, have an unallocated area in the middle of the disk, and it goes on like this up until the last recorded operation. After file operation 8330, we had to cut, as I said, and we also had some corruption after that, and then this unallocated area disappeared. But when the experiment ran as it should, we had this appearance. We don't know why. We have got different suggestions, for example that there should be a page file in there and other larger system files, but when we looked at all the machines and the different file systems in there, we couldn't find anything more than a few small allocations from our files and also some small allocations from system files, but the area is more or less empty on allocations, and it's in the middle. I know that in some blog I read that a long time ago at least, Microsoft divided a hard drive into two parts, and this might be a remnant of this. We will continue to pursue the truth and find out why it is like this. As you can see, the modern Windows 10 doesn't have this line, and it utilizes the disk slightly differently. If you look at the standard deviation, you also see that there are small differences between the two groups. Windows 7 has a more compact standard deviation pattern, and the Windows 10 starts at a lower value and increases rapidly, and then also has a more distributed appearance at the end. All of the standard deviations are rather high because they are placed at 2-3 million clusters in a total area of 16 million. So there are differences in the behavior of the allocation algorithms for Windows 7 and 10. In the maximum position, we see that for Windows 10 machines, the maximum position tends to be more spread out. This bold line shown is the file system utilization. As I said, it's the maximum size, or this cluster size of in clusters of a 64 gigabyte disk is approximately 16 million, yes. And as you can see, Windows 7 doesn't always use new areas. When the utilization increases, new areas of the disk is used, but Windows 7 continues to use maximum allocation positions well below the utilization curve. You also have the leeway effect. If we look at this utilization curve as a mountain range and the maximum allocation positions as clouds, they at the Windows 7 side slowly diminish and goes away as time goes. But on the Windows 10 side, they remain and behave more like a fog or something, staying in place. And you also see that Windows 10 does not use old maximum positions in the same way as Windows 7 does. So Windows 10 follows this bold line, this utilization line, in a much better way, which means that Windows 10 is more set to using new areas than Windows 7. We have also looked at the number of fragments and the differences there. And please also observe that the y-axis has a log scale. Once again, the number of fragments are slightly higher for Windows 10, which means that Windows 10 is more prone to fragmentation, or doesn't care if a file is fragmented in the same way as Windows 7 does. Otherwise, the maximum value of fragments are fairly alike. We see there are lines at the bottom where Windows 10 starts at about 50 fragments per allocation, and Windows 10 is somewhat below that. When we come to the mean fragment size, we have a few really interesting appearances. Windows 7 at approximately file operation 2000, which is, if we look at the bold curve again, the utilization curve, you see that it's about when a new level of utilization arises, and it goes about 50% utilization. Then the file system starts to behave in a different way, and we get a linearly increasing amount of or fragment size for Windows 7. So in a way, Windows 7 tries to keep a certain size, and it also notices that the sizes has to increase as we write new files, while Windows 10 doesn't care, once again, about the fragmentation in the same way as Windows 7 does. Otherwise, the mean fragment sizes are approximately the same for those outliers above. So, how should we conclude this? Well, first of all, we have shown that there are differences between Windows 7 and Windows 10 in how they allocate data. This is really good to know, because if we have a better knowledge of the behavior of the file system, we also have a better proof, a better value of our findings when we go to court. So the value of the evidence is higher in a way, because we can explain things. And also we can, in a way, actually see just from the allocation pattern which type of file system or operating system it is. So if it's more prone to fragmentation, if we lack certain things that the Windows 7 group has, we can draw the conclusion that it might be a Windows 10 machine, even though we can't find any file system data. We only have the raw allocated areas in the file carving, for example. So this can also be used in file carving to separate different file types and so on. As you know, you carve a file, you get a lot of fragments, and you have to put them together. Usually we don't know really what type of data there is, but from our findings we know that it's more probable to have a certain fragment size, a certain number of fragments, and so on. So we can draw conclusions from that and use that in file carving situations. We also, and that's, as I said earlier, is the main goal really of our experiments, we know in a better way where user data is placed. We know how the main allocation position slowly progresses towards the end of the data as the disk is utilized, but not as fast as we can think. And we also saw that the Windows 7 group is very keen on going back and using old already allocated areas, while Windows 10 isn't. And as I said, we can recognize the file system type from this data or this behavior. And we can also, in a way, maybe this is something we will pursue further, but there might be possible to, just from the pattern of the allocation, see if two files are written before or after each other. So the ordering of file writings, which can help us in improving the accuracy of timestamps and so on. And which without much further ado, I leave the floor open to questions. And are there any questions? Otherwise, I will say thank you for listening and bye.